In the last video, we defined what it means for a subset of a metric space to be compact. And in this video, we'll look at some properties of compact metric spaces. So a metric space E is compact if, as a set, it's compact. If E is a compact subset of the metric space E. In other words, what this is saying is that for every open cover of E, so an open cover of E means a collection of subsets of E, so this would be a collection of open subsets, but in this case, we don't have a proper subset of E. The set is just E, so it's a collection of open subsets of E such that E is equal to the union of the UIs. So for every open cover of E, there is a finite subcover of E. So a finite subset of this open cover that is also a cover of E. Okay. So we will look at some examples of compact metric spaces later, but let's prove this proposition that a closed subset S of a compact metric space, say E, is compact. So for the proof, well, we're trying to show that the subset S is compact, so we need to start off with an arbitrary open cover of S and show that it has a finite subcover. So suppose that UI for I and I is an open cover of S. Well, what that means is that S is a subset of the unions of the UIs, and UIs are open, right? So the UIs are open in E. Okay, open subsets of E. So S is closed. So let me draw a picture. So you have, let's say you have the real number line and you have some closed subset S. So you have some open cover of S. Okay. Well, the trick is to look at the complement of S. So you look at everything else. Well, the complement is open since S is closed. So since S is closed, the complement is open. Now you're given that E is compact. So the idea is to get an open cover of E and then use the compactness. So what we're going to do is take your open cover of S and then include the complement. This complement is open, and then that will be an open cover of E. So therefore, the set consisting of all the UIs union as complement is an open cover of E. So now by compactness of E, there's a finite subcover. So there is, well, so we have this cover which is potentially infinite collection of sets and then union this other set. So when you take a finite subset of that, it's going to be a finite set here, potentially including the complement, but potentially not. I mean, you don't actually know. But there is some finite subcover. But whether or not S complement is in the finite subcover, it actually, well, actually, S complement should be in the finite subcover, right? Because, well, I guess you don't know. I mean, it could be that UIs just cover S complement also. But at any rate, if you have a finite subcover, okay, that's going to be a finite subset of the UIs, possibly including S complement. So you could just say that E is going to be contained in some finite union of these UIs and S complement. So by compactness of E, there is a finite set J, a subset of I, such that E is the union of the UIs for I and J together with S complement. Okay. So now what do we do? We're trying to show that there's a finite subcover of S, right? So now we have a finite union. We've expressed E as a finite union. So what does that say about S? Well, S, so E is contained in this union, okay? But if you look at this last subset, S complement, S doesn't intersect S complement at all, right? So since S intersect S complement is then beset, what can we say? So if E is the union of a bunch of these UIs, right? And then S complement, and that makes up E, and then you have S, and S is a subset of E, but it doesn't intersect S complement at all, then that means that S must be in the union of the UIs. So therefore, and by the way, when I use the subset notation, it could be equals. Okay, I don't mean a proper subset. Right? So, and anyway, at any rate, we've now expressed S as the union of a finite number of the UIs, as contained in the union of a finite number of the UIs. So therefore, the set of UIs for I and J, and this is finite, this is a finite set, it's a finite subcover of S. So we started out with this arbitrary open cover of S, and we showed that there is a finite subcover of S. Therefore, hence, S is compact. So that's the proof. So let's review how the proof works. So you start off with an open cover of S, and the point is that since S is closed, S complement is open. So once you take that open cover of S and then include S complement, you get an open cover of E. And then since E is compact, E is covered by a finite number of those open sets, and then S doesn't intersect S complement, so S must be contained in that finite union. And that shows that you have a finite subcover of S. And that's the proof. So as a consequence, corollary, if F is a closed subset of E, and K is compact subset of E. So F is a closed subset of a metric space E, and K is a compact subset of a metric space E. Okay, of a metric space E. E is not necessarily compact. Then F intersect K is compact. Okay, why is this true? Well, F intersect K, what kind of subset is that? It's a subset of K, and it's the intersection of a closed subset with K. So therefore, this is a closed subset of K. And then by the proposition, since a closed subset of a compact set is compact, F intersect K is compact. Okay. All right. Great.